I'll be talking about building an authentication system that is resistant to rubber hose cryptanalysis. This is joint work with Daniel Sanchez, Paul Reber, Dan Boneh, and Patrick Lincoln. So for those who are not familiar with the term, rubber hose cryptanalysis refers to breaking security systems by convincing users into revealing their secrets. So both common sense and periodic media coverage tell us that this is a completely feasible scenario where either governments or underground organizations would not hesitate to use force. So to set up the discussion, imagine a secure facility where you need to authenticate yourself prior to entering, perhaps at the gate. There are a number of mechanisms in use today, from biometrics and hardware tokens to plain old passwords and PINs. And all of these are susceptible to rubber hose cryptanalysis. So biometric information could be recorded by an adversary, and fake credentials could be created based on that. Hardware tokens can be seized and stolen, and passwords, a user can be convinced to reveal those with not much difficulty. So what we're looking for, our quest, is for passwords that cannot be revealed consciously. So what we want to do is plant something in your brain. You know it's there, you know it, but you can't really consciously retrieve it. You can't tell anybody about it, even if you're willing to do so. So in order to explain the idea, we have to review the human memory systems. There are two types of those. One of them is responsible for storing facts that you can reason about with your brain, right? So you can think about formulas and events in the past and numbers and data and that's the declarative memory. And then there is procedural memory, which stores motor skills, things you can do like riding a bicycle, go there. And an important feature of that memory is that it's implicit, so to speak, or you can't actually retrieve stuff from it. You can't retrieve facts and think about them. You can execute those motor skills, but that's about it. So to summarize, what we want to do is design a game where we teach the user a particular skill or a particular flavor of that game, and then authenticate the user by measuring the skill that they're supposed to have. So Guitar Hero is a good template to build this on, for example. So you have a practically unlimited set of songs that you can teach users to play on this device. You have these objects that move down the screen, and you have to intercept them by pressing the right keys. So you're building a motor skill there, and you can think of each song as your credential, right? And then you measure users' performance, you score them, and that's your authentication. So I would like to show you a video, if this will actually work, of our authentication game. Let's see if it loads. I hope it does. If it does, yeah, okay. So first there is a, oops. Sorry about that. First, there is a privacy notice that we show that the user has to click through because this is an experiment involving people. And then the training phase of the game starts, where little balls, little circles move from down the screen, and then you can see that the user is intercepting them, sometimes correctly, sometimes not correctly. And over time, the user will get trained on a particular sequence, and then after that we can test the user. So the game is designed in such a way that while you train, it will try to maintain a specific ratio of 70% correct keystrokes. Right? So 70% of these interceptions, it will try to get to a point, to a speed at which 70% are correct. So if you're too good, it will speed up for you so that you'll start making some mistakes. If you're not very good, it will slow down so that instead of getting frustrated, you will actually get something out of this training. You'll learn your sequence. The cost of this, for the training, that takes about 30 to 40 minutes, and authentication is 5 to 10 minutes currently. So clearly, this is not something that you would do every day. When you get in the morning, you get to work, or when your screen locks up. But in certain environments where there's, the stakes are high, you need additional security. This, in this current form, might be justified, and potentially after improvements, these numbers could start looking better. So the concept in neuropsychology, which this is based on, is called serial interception sequence learning. So this is a task that people use in order to explore properties of procedural memory. So in particular, the game selects a sequence for the user, and we'll talk about what that sequence looks like in just a little bit. Then the user trains on it, and then there's a test. And the test is done by, again, measuring percentage of correct keystrokes. But while the game still tries to stay at the 70% ratio, because we feed the user pieces of trained sequences and pieces of random other unknown sequences, the user will exhibit a different level of performance on those, and we can compare them and decide whether that pattern matches what we expect for the user. We can also test the user explicitly and ask them how familiar different sequences are. And based on that, we can conclude that users don't recognize their sequences in explicit tests. So this is really important and a really interesting fact, that you can ask them, and they can't really say with much confidence what it is that they saw. One quote from a user in one of the runs that we had is that when I played, the tempo was so high, it was incredibly difficult to keep a track of the circles. Most of the time, my fingers moved by themselves. At least it felt that way. So this is exactly what we're trying to achieve here. We're trying to not let them think while they play. And you can see that the game has achieved its goal by adjusting the ratio, adjusting the speed so that it's high enough for this player that they can't play perfectly. They have to have some mistakes. They have to make some mistakes while they go. In the recognition experiment, you can see that this is the explicit recognition. This is where we ask users how familiar they are with their trained sequence and with 4 other random sequences we select, right? In order to see if they can recall what is it that they learned, so that, for example, if they get forced, we want to know if they can reveal their own sequence. So you can see there is a little bit advantage for the trained sequence here. It's only about 1 point out of 10. So on a scale of 0 to 10, they will rate how familiar different sequences are. So you can see the trained sequence has a little bit of an advantage. And this is expected because people will tend to sometimes see little patterns. And based on those, they might recognize one sequence and give it a higher rating than others. But you can still see that even the non-trained sequences got a pretty decent level of recognition, right? These are false positives, basically. So how do we create the sequences? There are a couple of constraints that we use. And those constraints are designed to make it harder for the user to notice anything about the sequence they're training on. So first of all, we want a uniform distribution of each individual character. So no character appears more frequently than others. We also want uniform distribution of pairs. So successive pairs of characters, we want them to appear equally often. In particular, for the sequences which we select for users, we want each pair or bigram to appear exactly once, with the additional condition that the same character can't be repeated. So you want pairs of different characters appearing consecutively. So 6 by 5, that's 30 characters in a sequence. And each of those sequences maps one-to-one to a cycle, to an Euler cycle in this graph here. This graph has edges which map to characters that appear one after the other. So you have exactly one edge for f going to s. And in the Euler cycle, you'll have to traverse that edge exactly once. So that tells you that the resulting sequence you get out of traversing the graph will have the properties we listed on the previous slide. We can estimate, or actually we can calculate exactly how many such cycles exist for this graph. They're this number, which we are given by the best theorem, which is used for establishing the number of Euler cycles in directed graphs. And this number is approximately 2 to the 37.8, which means there are 37.8 bits of entropy. So if we select a credential for the user, we're selecting it from a large set of this size, which makes it pretty good in the sense of providing security as a password. So we've run experiments, first of all, to demonstrate that the user is learning the skill. So we saw that retention, we saw that explicit recognition is fairly poor. However, what we see here is across 3 experiments, denoted by the blue bars there. Each of these is a separate batch of users. We test those users immediately after training. And the blue bars show the advantage of the trained sequence in terms of % of correct keystrokes over the non-trained ones that we show to the user. So we see for immediate testing, we see between 7 and 10% of advantage for the trained sequence. And then for 2 of those experiments, 2 of the 3 experiments, we actually repeated the test with the same users a week and 2 weeks later. And we measured the advantage for the trained sequence, which we recorded from the training session. So we know what that user trained on. We let them play that again in a week or in 2 weeks. And so we see between 6 and 7% advantage for that. So you can, obviously over time, the skill decreases. So you tend to forget whatever it is that you trained on. But the expression is still there, so we can still measure it. We can still authenticate the user. We could do more tests in the future, which establish when is it that that level of skill goes down to a critical point where we need to do retraining for the user. That's something additional we need to do. Here we've also run some experiments where we try to assess how feasible is it for an attacker to capture a user and estimate their knowledge by showing them fragments of sequences. So the first thing we did was show them triplets of characters, so triples or trigrams. And we tried to see if we show them all of the trigrams, perhaps the ones that they trained on will have a better expression than all the others that they're not supposed to have seen all that much. And what turned out is that actually that's not the case. So the trigram distribution was pretty uniform. The trained trigrams are distributed evenly in the overall ranking. So an attacker trying to profile a user in this way has very little to gain. They can't really estimate anything about the sequence that the user was training on. Now, we got some more recent data that we haven't fully analyzed yet. But what it's showing is that if you're showing larger fragments of what the user trained on, you will actually see improved performance. So the user starts exhibiting performance the longer the sequence fragment that you're showing them. And this is expected, right? So at the full sequence length, our users are exhibiting learning, right? They're training they're improving on their own sequence. They're not improving on all the random sequences they haven't seen. Right? So somewhere in the middle, we expect that skill to start showing. So it turns out that it's showing even at the length of 4 and 5. So fragments of size 4 and 5 show some learning. It is still not clear whether an attacker can use that to their advantage to reconstruct the sequence. So what we would need to do for that, and these are bigger and more time-consuming for the user experiments that we still need to run, is to show them, for example, all the fragments of size 4 and see for the ones that appear in the sequence what relative place do they have in the overall rankings. We actually expect that those will be biased towards the top, but there will be still enough of a noise in the results that it would make the attacker's life very difficult. We don't know that yet. There's also an opportunity in this that we actually might improve our testing so that when we test the user, instead of showing the full sequence, we test them on different fragments, possibly of different sizes, and by that we could reduce the risk of eavesdropping. Again, this is something that is work that we could do to improve this. So we'll shift gears a little bit, talk about the experiments and how we did them. We used a mechanical Turk, which has the advantage, it gives us a large number of available subjects for the test. We use only about 370 users in our experiments. We only use unique users because we don't want any interference. But the big thing, the big win for us in using the system over the status quo, which is recruit people for several weeks and then run your experiment, you get 20 data points and then you analyze them. What we do is we actually post our experiment in the evening, we get the results in the morning, we can iterate really quickly, and then over the course of several days we improve the experiment and get some really good results. So this is really nice. This is something that we feel is will be useful to other people as well as a technique. So this is how it looks like, what the workflow looks like in Amazon. The workers see our task description, they accept it, then they play it in a frame hosted by our own servers. So this is called an external intelligence task in Mechanical Turk. And at the end of it, we provide the user with a code, which they enter in the Amazon interface. So that code is used by us later on to match user claims that they finished work, they need to get paid, with the work that they did. And we can use this to make sure that they actually did a good faith effort. They didn't try to cheat in some way. And eventually we authorize payment for some of them and then reject others. So in order to round this off, we have to talk about abuse that we've seen in these experiments. We've had to reject only about 5% of the submissions. This is pretty good. This is much better than what we ever expected. And to a great extent, we believe this is due to the reputation system that Amazon has, where users have to have a good approval rate, so they try to do well in the jobs that they take. Out of the ones that we reject, we most often see random or empty receipt codes submitted, which tells us that the user accepted the task. They saw that we're paying well for it. They accepted it, but then they somehow didn't want to do the work, and they wanted to see if we'll pay anyway, and we don't. And then the other two types of abuse are we see submissions, but they have a lot of repetition of wrong key presses, which tells us there's some automation. I've asked people several times by email whether there's anything like that, because they also usually come back and they complain because they don't get paid. And we've asked them, but they say they don't have anything. I don't know. Maybe it's a bot or something. But then we also see large stretches without any user activity, which tells us they probably, forgot about the window, and I don't know. Maybe they were trying to let the game finish on its own. But that's what we typically see. In any case, the rate is fairly low. There's some related work that we have to mention. Some of it deals with using implicit memory for providing either password recovery methods or just assessing the feasibility of using implicit memory for passwords. Most of this work deals with large sets of images that the user gets primed on. And the difficulty with that is that you somehow have to obtain those images, and then very often the image set is single use. So the moment you try to test users with specific images, you can no longer use them in the future. So this is kind of a very serious constraint. What we've done with our work is devise a way to generate these credentials from a very uniform set, and the credentials themselves are compact. So they're much closer to a key in AES, if you will, than to a one-time pad, right? So that's the analogy I would use. We have a better representation, which is more manageable, which lets you not worry about the actual domain of the credentials themselves and worry about how to use them instead. The other line of work has been about measuring motor skills, like, for example, keystroke timing, and that has a long history. Most of that work is done in the context, it's done in a way that it's much closer to a biometric measurement rather than a password, in the sense that keystroke timing is something that you would assume is a static feature of every individual user. So even though you can tell users by that, there's no clear answer about how you would change your keystroke timing if you want to change your password. What we provide is a system where you can do this. So we provide the full password semantics without the coercibility, if you will. So in summary, we've shown how we can build a system that uses passwords for authentication, passwords that cannot be extracted from your brain, including by yourself, but can be also reset if needed. And then in future work, we hope we can actually make this part of your brain, which stores procedural memory, to actually do a little bit simple computations. And what that would enable us to do is actually implement a challenge response protocol. That would be very interesting. And it would actually take care of the eavesdropping issue. We also feel that using complementary data, like EEG data from sensors on your skin, might be helpful either to speed up authentication or make the process more reliable, more secure. So this is another direction which we feel progress can be made in. And I'll end with a cartoon, and I can probably take some questions. We can hear.
Okay. Hi, Yossi Oren, Tel Aviv University. Thanks for the great talk. I have a biology question, perhaps you can answer. Are my eye motions correlated with my sensor activities when I'm doing all these repetitive motor tests? Because it seems like if I have a webcam trained at the eyes of the user, I can get much more data. And if the user is, I don't know, arthritic or old or clumsy, I can still get some good data. But the question is, if you're typing by yourself, are you still using your eyes in a repetitive, predictable way?
Yeah, interesting. We don't know. It's a good question, right? We haven't tried to correlate that and measure the eye movements, but certainly along the lines of using EEG data or other sensor information, looking at the eyes or figuring out where you're looking at, that would be a good thing to explore. Okay. And the good thing about this topic is there's so much more to do. We're scratching the surface, really.
Thank you.
Paul Van Oorschot, Carleton. First, just about related work. I guess the work on mouse dynamics might also be of interest. But the question I have is, I didn't quite get the threat model. So if I have a user ID and I was logging in, how much of the full sequence of a user would I get? Because I guess if I could capture enough of it, then I could go off and train myself for 30 or 40 minutes.
So we have some assumptions there. Basically, if you're authenticating, at the moment, we depend that you cannot record that session, the authentication session. So we require the user to be present on the spot and just, play.
Okay.
And
so it's a supervised login then?
Yes, at the moment it is. And also, I mean, the other side of this is we also can't allow you to do remote authentication because somebody could be forcing you to play the game. We can't see that if you're miles away at a terminal. So that's the other constraint. You have to be physically present.
Thank you.
Ian Goldberg, University of Waterloo. So you were targeting a 70% hit rate on the letters that. What's magic about the number 70?
Well, so you can probably vary it a little bit, but essentially we don't want the game to be aiming for you to do really poorly. We also don't want it has to be somewhere in the middle, because if the percentage is either very low or very high, then what we'll see is that the data will be too uniform, so we won't be able to distinguish between, so somebody who's good will be good both on the trained sequence and on random other sequences, right? So at that point, we won't be getting any interesting data from testing them, right? So we want them to make enough mistakes. Within that, there is room to play, but previous work in the neuropsychology domain was using similar percentages, so we just went along with that. I mean, it's not, I don't think 70 is a magic number.
Okay, thanks.
Yeah.
Hi, I'm Stefan Surio from Microsoft Research here in Redmond. So I have a clarifying question. On your last slide, you said that this form of authentication can be reset. What do you mean by that?
Oh, so what I mean by that is that if you want to, if we're claiming to provide something which is equivalent to a password, a password you can change, right?
Right.
So there are similar mechanisms that people have investigated, like the timing of various events as you use your computer, which are not readily reset, right? You can't, or at least people haven't looked into how do you reset the timing of your keystrokes on the keyboard, right? And if you don't answer that, then it's more like a biometric, right? It's something fixed about how you use your computer that you can measure, but you can't really change.
I see.
So we're answering how can
So
you
basically
change
you're saying with this form, with this solution, I can retrain the user with sort of a different password.
Yes.
But just to be clear, you don't mean that in case somehow I forget this kind of password, because you'll be able to reset me somehow.
Exactly.
Right?
No, it's just not about password reset or any. Yeah,
but any form of authentication, you need to have a form of password reset to it, because especially with things like this, I might, something might hit me and suddenly I'm becoming untrained overnight.
But that's equivalent to the case with a password. If you have a password that you know consciously, it's the same thing, right? You might forget it.
It is, but for passwords, the way you reset them, you also use sort of a different password to reset your previous password. So but password reset is as strong as the original authentication scheme. So it'd be nice to have a reset mechanism for this thing that is as strong as the original scheme.
Yeah, agreed. And in reality, you will probably use this in conjunction with another method, right? So this is probably not going to answer the whole question, but yeah.
Ian Myers, Johns Hopkins. Do you have any idea how you might extend this work to the actual scenario on that slide where you're using it for key derivation?
Let's see, for key derivation. So it's a little bit imprecise to be used for that. We haven't really looked at the encryption, right, in the case where what the user enters is used. I mean, in this system, we depend on the system actually playing a sequence to you, right? So the system needs to know what to play, and you're strictly demonstrating your skill at what you're shown, right? So you don't create anything yourself, right? You don't provide a key on your own. So it's not clear how it would be used for this scenario. This is more to illustrate the dangers of relying on a system without considering the effects of $5 wrenches and such other tools.